Morning, everyone. Welcome to lecture number 12. In this lecture, we are going to discuss some mechanical properties of concrete, such as multi-axial strengths, stability tensile strengths, elastic modulus, and also viscoelasticity of concrete materials. Okay. Multi-axial stress. When we do the compression test of a concrete cylinder, we have vertical load, which is provided by the steel plate in the top and bottom. Okay, and we know from last time, concrete failure caused by tensile stress generated from compression. Because when we compress the concrete in a vertical direction, in a horizontal direction, we have expansion. This is because concrete has a Poisson's ratio of around 0.18, 0.2. Okay. If we have more than one axial stress, like in this example, we have vertical compression, but lateral tension. So that will reduce the accuracy because that will increase the tensile stress in the horizontal direction. Okay, so the concrete will crack earlier. On the other hand, if we have compression in the lateral direction, okay, so this is acting as a constraining effect provided by the two steel blades under the compression test. So that will confine the concrete from expand in the horizontal direction. So that lateral compression will produce higher compressive strength of concrete. Here talk about tension testing. Okay, so for typical materials, if we want to measure the tensile strength, we want to pull the material apart. Okay, so we measure what's the force to pull the materials and also divided by the cross section. Okay, so this is called direct tension test. Okay, based on that, we can easily calculate the tensile stress, which is P divided by the cross section area A. Okay. However, we rarely use direct tension test for concrete. That is because we need the instrument to grab the specimen, and that grabbing force will generate some stress concentration, which will affect the field result. Because of that, instead of doing direct tension test, we do a so-called split tensile stress or split cylinder test. So we have a concrete cylinder, okay, and we compress the cylinder along the diameter direction, okay, like this. And in the top and bottom section, we have compression. But in the majority of cross section, we have tensile stress. Okay. And based on that, we can calculate what is the tensile load, or what is I prime SP, which is split tensile stress. Okay, so this is based on the maximum sigma 1 the cylinder can resist. Okay, P is load, L and D is the diameter and the length of the specimen. For flexure testing, we could have either the center point. Okay, we have two support in two ends, and we have load in the middle span. Okay, or we could have so-called third point. Again, we have two support at two ends, and we have half P and half P in the 1/3 and the 1/3 part. Okay. The stress level can be calculated based on M. M is the moment generated by the P. Okay. And the C is distance from the point of interest to the neutral axial, which is in the middle cross section here. Okay. And I is called moment of inertia. We learned that from CE370. Okay. For rectangular shape, the moment of inertia is this. Where B is the width and B is the depth of the cross section. Okay. So based on these equations, we can calculate the stress level at any point in the beam. And the moment of rupture is the maximum stress level. Okay, calculated based on the load P and also dimension of the beam. Okay, so the moment of rupture will affect by the size of the specimen. Okay, as we can see from here, if we increase the depth of the specimen, the depth is the height of the beam. Okay, so we increase the depth, we increase the size of the beam. So we have more materials in the larger beam. So as a result, the chance the concrete material has flaw and also the size of the flaw is also higher. Okay, we discussed that in last lecture. Okay, the strength of concrete. So we increase the depth of the specimen, the moment rupture will be decrease. Sorry. And the sigma, maximum sigma is higher than the direct tensile stress because the so-called strain gradient. Okay, so I can explain what is strain gradient. Okay, so for a stress and strain curve of this beam, okay, we can draw something like this. So this is the epsilon strain. This is sigma stress in the x-axis. Okay, so if the material is pure elastic materials, okay, the stress and strain curve will be something like this along a cross section. Okay. However, okay, because concrete material is not pure elastic materials, okay, the actual stress distribution will be something like this. Okay. So the stress level, so here is a stress. The stress level at the top and bottom will be actually smaller compared to what we can calculate based on pure elastic materials. Okay. The reason again is because concrete is not a pure elastic materials. We call that strain gradient. Okay. So this is actual stress. Okay, so the actual stress is lower compared with the stress level we calculate based on classic mechanics of materials, assuming concrete is pure elastic materials. Okay. Okay. This slide shows some correlation which is not very accurate between the compressive strength of concrete and other hardening properties. Okay, so this is based on ACI. ACI is the American Concrete Institute. Okay, if the compressive strength of concrete is F prime C, we can estimate the elastic modulus of concrete based on this equation. Rho is the density of concrete, which is around 150 pounds per cubic foot. Tensile stress, okay, we can use this equation. Okay, another rough estimation for tensile stress is around 10% of compressive stress. For fracture strength, we can use this equation. For Poisson's ratio, typically concrete is around 0.18, 0.2. Okay. Yeah. Okay. Before we further discuss the mechanical property of concrete, let's review some of the basic information. Okay. The stress and the strain relationship. The stress, we also call sigma, right, is defined as the force divided by the cross-section area A. Okay, and the strength at prime C is the measurement of the maximum stress the material can take before failure. And the strain we call epsilon is delta L, which is change in length divided by the original length of the specimen, L0. Okay, and elastic modulus E value is equal to the stress sigma or the strain epsilon, which is also the slope of the stress and the strain curve. Okay, so everybody knows this already. Right. If I assume the material is a pure elastic materials, okay, and this equation holds true. Okay, so Poisson's ratio, we discussed this in last lecture, is equal to the absolute value of epsilon y, which is the strain in the y direction, the horizontal direction here, okay, divided by the strain in x direction. Okay, keep in mind this is absolute value because the strain could be positive or negative depending on whether it's compression or tension. Okay, and if we have multi-axial stress, the strain in one axial is the combination of the strain from other directions. For example, this is the stress from x direction over the E value minus this is Poisson's ratio. Okay, so we can see from here the stress coming from the other two directions also contribute to the strain in the x direction. And same thing here for y and z direction. Okay. And here shows shear stress. The shear stress tau is equal to G, which is shear modulus. Okay. Gamma is the shear strain. Okay. The shear modulus is a function of E value, modulus of elasticity, and also Poisson's ratio of concrete. Okay. So again, this is by assuming the material is a pure elastic material. All right, so more elasticity principles. Okay, so if we consider a unit element with length, height, and width equal to 1, okay, so the total volume of that unit is 1 times 1 times 1, so that's 1. Okay, so if the unit take a load, so we have change in length. Okay, so the new volume will be new length 1 plus epsilon x, which is the strain in the x direction, times 1 plus epsilon y times 1 plus epsilon z. Okay, but this strain is much less than 1. Keep that in mind. So the volumetric strain is equal to the change in volume, which is equal to final volume minus initial volume of the specimen, divided by initial volume. Okay, so you plug in this information into this equation. So the volumetric strain is equal to the strain in x, y, and z direction added together. Okay, again, the strain in this direction could be positive or negative, depending on compression or tension. Here, HOTS is called higher order term of strain, such as epsilon x times epsilon y. And we can just ignore this because epsilon x, y, and z are very small, much less than 1. And epsilon x times epsilon y will be much less than 1. So we can just ignore this HOTS. So the volumetric strain will equal to epsilon x plus epsilon y plus epsilon z. Okay. In a special case, we call it hydrostatic stress. The stress level is coming from all the 3 directions, and stress level is the same. So sigma x equal to sigma y equal to sigma z. Okay, so this is similar to when we put a specimen under water. So that's why we call that hydrostatic stress. Okay, in this special case, the stress level is equal to K epsilon times epsilon V. Okay, K is called bulk modulus, which is also a function of E value and Poisson's ratio. Okay. So again, these last 2 slides are review of classic elasticity principles. Okay. However, concrete and many other materials are not pure elastic materials. Okay. As we can see from here, this curve shows us the load and deformation curve for metals, glass, concrete, and rubber. Okay, and the load and deformation curve are quite different for these materials, as we can see from here. But for glass, the green curve, okay, we can see the slope of the curve is very constant. Okay, which means the E value does not change when we increase the load. Okay. However, at peak load, glass will just break. Okay, so after peak load, glass will fail suddenly and cannot resist any load. Okay, and we call this type of materials brittle materials. Okay, so brittle materials such as glass has very small inelastic strain before failure. Right. For rubber and also metals such as steel, okay, these materials initially also has an elastic region, okay, because the slope is constant. So this is metal, this is rubber. Okay, from here to here, the line is almost straight. Okay, so this is called again elastic strain. But after that, we have also inelastic strain. So metal has a lot of inelastic strain before failure at this point. And rubber can take more load up to here. So both metal and rubber have very large inelastic strain before failure. All right. For concrete, we call that quasi-brittle materials. It's kind of brittle, but not as brittle as glass. Okay. So concrete has some elastic region. Okay. Then we have inelastic region. At the peak load, the concrete can still resist some of the load before final failure. Right. And this table showing us the E value of concrete, steel, glass, and rubber, as well as the strengths. This is the tensile stress, and 35 is the typical compressive stress of concrete. Okay, Poisson's ratio for concrete, steel, glass, and rubber. Okay. Another new words we should discuss here is called toughness. Okay, I'm not sure if you have you know these words before, but here in mechanics of materials, toughness is defined as amount of energy required to fracture a specimen. Okay. In a load and deformation curve, the toughness can be easily calculated as the areas under the curve. For example, the toughness of metal is the areas underneath this black curve. Okay, because again, toughness is energy, and energy is equal to force, which is load, times distance, which is deformation. So by compare the areas under the curve, we can easily tell metal has the highest toughness, okay, higher than glass, concrete, and rubber. All right. So based on the failure mode, we could have these 4 classifications. Okay. For brittle materials, first of all, for all the materials, they have elastic region at the beginning. Okay. But for brittle materials, after elastic region, there's no inelastic region. Okay, there's a sudden failure after at the end of elastic region for brittle materials such as glass. Okay. Concrete belong to so-called strain softening materials, which means after the elastic region, the concrete or other strain softening materials can still resist some kind of load, but that load is lower than the peak load at the end of elastic region. Okay. On the other hand, strain hardening materials such as steel, after the elastic region, the resistance will goes up. Okay, so we have a higher resistance after the load here. Right. If the resistance does not goes up, goes down, keep constant, we call that elastic, perfectly plastic materials. Okay, and I cannot give an example of that type of materials. Okay, so in series, that material does exist. So next, let's look at viscoelasticity. Okay, I mentioned that before, concrete is not pure elastic materials. Okay, actually, concrete has both elastic component and viscous component. So let's look at what is elastic component and what is viscous component. So let's assume a load is applied at time t1 for all the 3 materials, and the load is removed at t2. Okay, and look at the strain and stress and time response of different types of materials. For elastic materials at t1, we apply the load, so we can see the deformation is instantaneously. After the load is removed at t2, the recovery is also immediately. Okay, you have recovery instantaneously. For viscous materials such as honey, okay, at T1 we apply the load. Deformation is dependent on the time, so slowly increase in the strain. At T2 we remove the load, the strain will not go to 0 immediately, like in the elastic materials. So the strain will keep their constant. So the deformation is time dependent and is not completely recovered after the stress is removed. Okay. Some materials such as concrete has both elastic behavior and viscous behavior. So at T1, some of the deformation is instantaneous and part of deformation is not, is time dependent. At T2, we remove the load and part of the deformation recovery is instantaneously, but part of recovery is time dependent. Okay. So concrete actually behave somehow like this. So for viscoelastic materials, how fast you apply a load does matter, okay? Because the deformation and the recovery, part of them are time dependent. All right. Then let's look at the rate of loading and its effect on viscoelastic materials such as concrete. Okay. So here shows a rate of loading for different type of load. Okay, from creep to blast, the strain rate differs very much. Okay, so the unit of strain rate is 1/2, which is defined as this. Share my iPad. Okay, the rate of loading is defined as the deformation speed, which is in the unit of meter per second, divided by the length of the specimen, which is in the unit of meter. Okay, so as a result, the unit of strain rate will be 1/2. Because concrete is viscoelastic properties, the deformation is also time dependent. When the load rate is fast, okay, the deflection will be smaller compared to the same magnitude of load, but the load rate is slower. Okay, so faster load, we have smaller deflection. Okay, again, because the viscous component of the concrete is time dependent. Okay, the faster the load, the deflection will be smaller. Okay, and if we keep the load constant on concrete, for elastic materials, the strain should not change because we do not change the stress level. So constant stress level, we have constant strain. But for viscoelastic materials such as concrete, the strain will slowly goes up. Okay, we call that creep. In the figure here, we keep the strain constant. Okay, we keep the strain of the material constant, and we measure the stress level inside the specimen, and we can see the stress level will goes down slowly. Okay, we call that phenomenon relaxation because the stress level relaxed a little bit. Again, this is because the viscous component inside concrete. Okay, so creep and relaxation is the nature of reinforced concrete, and we're going to discuss these phenomena in future lectures in much more details. Right, we showed these slides before. Here shows the typical compressive failure for concrete materials. Again, initially we have elastic region. Later on, when we have micro cracks generated, concrete become viscoelastic. Okay, so the slope will change, become smaller, which means the E value become smaller. Okay, and depending on the friction provided by the steel plate in the top and bottom, we could have different fracture surface. Without friction, we have straight lines, and with friction, we have so-called cup cone shape. All right, let's look at the cracking process of concrete in details. Okay, so initially, again, we have elastic region. This is around 0 to 30% of I'(C). Okay, so we have very little cracking in the ITZ. So why we say it's cracking in ITZ? Because normally the weakest link in concrete is the ITZ, which is the boundary between the paste and aggregate. Okay, so the crack will first generated in the ITZ area. Okay, so when we further increase the stress level, as in this green zone, the crack in ITZ become more severe. Okay, and also we have more cracks generated in more area. Okay, this is between 30% to 70% of per-PM-C. Beyond 70% of per-PM-C up to per-PM-C, the cracks in certain location will opens up. Okay, as we can see here, cracks in this location opens up. However, cracks in other locations does not change as much. Okay, so we call that crack localization. Again, cracks in certain locations are growing much larger than other locations. And after the IF'(C) starting the load, cracks will open up in this certain location. Concrete in other location can still take some of the load, even though they also crack, but it's not total failure in these regions. Let's talk more about ITZ, all the boundary between the coarse aggregate and the cement paste. The strength of the concrete depends on cement paste. Okay, all the ITZ, typically, I say typically because for high strength concrete, the weakest link could be aggregate. Okay, so ITZ, we also call that interfacial transition zone, is again typically the weak region. The surface texture and also the shape of aggregate will affect this bound. Okay, the rough surface, the strength could be up to 6% higher. Okay, the bound will also increase with lower water cement ratio, or we add more silica film in the system. Okay, so silica film will transfer the calcium hydroxide into CSH, so strengthening the ITZ zone. Lower water cement ratio will also make the ITZ denser. Okay, so this will increase the strength of ITZ. Okay. The different E value, the different modulus of elasticity between the aggregate and cement paste might lead to cracking. Okay. Typically, the E value of aggregate will be higher than the E value of paste. So when a concrete is under compression, imagine aggregate is stiffer compared to paste. Okay, so we have stress concentration along the boundary between the aggregate and cement paste. So that is another reason crack will generate at ITZ. And because of that, let's look at the fracture behavior of cement paste, mortar, and concrete. Okay. For paste, we only have cement plus mixed with water. For mortar, we have cement paste plus sand particles. And for concrete, we have paste, sand, and also coarse aggregate. Okay. So assume all the material has the same water to cement ratio and other mixed proportions. The crack patterns for cement paste is almost straight because we only have one homogeneous matrix, the cement paste. Okay. For concrete, because we have cement paste, we have aggregate, and we also have ITZ. Okay. Depending on what is the weakest link, the crack will first generate around the ITZ or the paste or the aggregate. Okay. So then the crack will go around the stronger region and connect the weak region. As a result, the crack will not be a straight line like in a cement paste. For mortar, it will be somewhere between the cement paste and concrete because mortar only have small particles, small sand. Okay. So again, here shows what is localization concept. After concrete damage at the peak load, only certain areas is damaged, and we call that damage zone. In the damage zone, okay, the resistance to load becomes zero. Okay, but for other zones is undamaged. When you release the stress, it is behave like elastic materials. The strain will go back to almost zero. Okay, so this is the reason why concrete can still resist some of the load even after the peak load is achieved. So post-peak behavior, or the behavior of concrete after the peak load is very important, okay? Because in most reinforced concrete, we have steel rebar, okay, and concrete. For example, this reinforced concrete beam, the rebar is here, okay? If the beam is under bending moment, okay, and here is the stress level. And based on classic mechanics of materials, we can calculate the stress level at any point, right? So here we have highest stress level, and here the stress level should be zero. Okay. However, at top the concrete will crack. Okay. When concrete crack, the concrete will not fail suddenly. Some part of the concrete can still resist the load. So the actual stress distribution will be something like this. As a result, when you do reinforced concrete design, when you calculate how much stress the beam can resist, we do not assume a triangle shape. So we assume a rectangular shape. Okay, so we will learn more about this, how to design reinforced concrete members in future classes. I think in 381 or 481. Okay, and here shows a reinforced concrete beam. Okay, but still we work together with concrete, even though in some deflection level, the concrete passed the peak stress. Okay, the concrete can still work together with the steel to take the load. And here shows continuous beam. Okay, the moment diagram will be something like this as the blue line. But in some areas, such as in the middle span, the stress level will be the highest, and also here. So the concrete there may be cracked, but after concrete crack, the reinforced concrete slab can still resist some load. And the moment will be redistributed due to this cracking. So post-peak behavior is very important. It is crucial for reinforced concrete to work. Okay. All right. So here shows more post-peak behavior of different type of concrete. For normal concrete, after peak load, it can still resist some of the load until the total failure here. For high strength concrete, the strength is higher. Okay, but high strength concrete typically is more brittle compared to normal concrete. As we can see from here, we have almost sudden failure for high strength concrete. Okay. If we put fibers are thin fibers made of polymer or steel fibers, okay, to increase the toughness and also ductility of concrete. So we'll have a future lecture talk about fiber reinforced concrete. When you put fibers in concrete, it will change the load and displacement behavior of concrete totally. Okay. As we can see from here, the ductility will increase. Okay. The toughness will also increase. Some of the fiber reinforced concrete, the I'(C), the peak load will also increase. Okay. All right. Okay. So the key idea for this class, how does crack develop during failure? So depending on the type of materials, the failure mode will be different. Okay. So concrete is brittle or ductile materials. So concrete is so-called quasi-brittle materials. Okay. So why post behavior is important? Okay, we just discussed that. And this is the reading suggestion for this class. And that's it.